now that we understand interpreting the coefficients from a Poisson GLM, let's move on to actually the p-values and the kind of goodness of fit, the d-squared values that we talked about before, right? Looking at that summary of our GLM object, we see that as before with any GLM, there is no p-value for the model and no r-squared value because they can't be calculated for GLMs because of how GLMs are fitted. And so we need to get that LR test function from the LM test package. So call up that package and then apply the LR test function from it to our GLM. And here we can see that our model has a significant p-value, right? Chi-squared equals 41.02. We've got 2 degrees of freedom and a p-value of 0.0000, very small. So this significant p-value is telling us that our result is unlikely if the null hypothesis were true, right? Again, a likelihood ratio test, like this LR test function is doing, is comparing our model to an intercept-only version of the model. Right? So our model is missing elements as a function of location, and the intercept-only model is just missing elements as a function of 1, which denotes the intercept. And so because our model, if we look at the summary, has 3 total coefficients, intercept, Japan, and Ohio, the intercept-only model only has 1 coefficient, intercept. This means that the degrees of freedom is 2. As I said before, it's -2 in this output because it's subtracting in the way that it's taking our model, which has 3 parameters, and subtracting the 1 parameter of the intercept-only model, and that leaves us with 2. The chi-squared test, then, you report that, you report 2 degrees of freedom, and you can report the p-value is less than 0.0001. This, of course, is important to remember that this is how you get the p-value. When you're looking at the summary output, right, each coefficient estimate has a p-value that's expressing its difference from 0, but those aren't the p-values you want here, right? Especially because there's 3 of them here, and you just are looking for the overall model p-value. That's where the likelihood ratio test comes in. This is kind of the equivalent of using the ANOVA function on an LM object. It tells you that location, not specifically which location, but that location in general has a significant effect on predicting this missing number of elements that we're dealing with. Now let's look at the d-squared function. Remember, this is from the mod EVA package, and we want d-squared of our model, and we can see that it's a d-squared value of 0.073. This is a very weak effect, right? Only 7% of the deviance, of the total kind of deviance between a perfect model and an intercept-only model, only 7% of that deviance is explained by including location. So we might have gotten a significant result, but the model still isn't doing all of that good of a job. It's not practically a very significant thing. But if you only really care about kind of the same questions that an ANOVA answers, if you really just want to know whether, go back to the plot here, whether there is a difference in the number of missing elements between these 3 groups, what you really care about then is the p-value more than the d-squared value. It just tells you whether there's a real or statistically unlikely difference or not. And so it's kind of fine to rely on the p-value in this context if that's all you're really interested in. The d-squared value is important, though, because it does tell you that the location really isn't predicting the missing value all that well, but there is a significant difference in missing value between these 2 groups. That's what the p-value tells us. So depending on what your question is, that kind of might be more relevant for you. Now, just like with an ANOVA, we still don't know which locations are different from each other, right? Is this significant result being driven by the Alaskan missing elements, the Ohioan, the Japanese? What's going on with that? we can run a post hoc test, right? We got a significant result. We know that there's differences between these three groups, but we don't know which groups are driving it. So that's what a post hoc test is for. Now before, with our post hoc tests, with an ANOVA and a linear modeling, we just ran a pairwise t-test with a Bonferroni correction because we're running multiple comparisons, so we're screwing up our p-values and we need to control for that. And so here we can do kind of a similar thing. What we're going to do is use a function called GLHT. This is a function that's in the package multcomp. You might need to install this package if you haven't before, and then once you install it, load it with the library function. Again, it's multcomp, standing for multiple comparisons. And with this package, what we're going to do then is use the GLHT function, which stands for General Linear Hypothesis Test. It's just a kind of post hoc test that works for generalized linear models. Because we couldn't really run pairwise t-tests because, again, we're in generalized linear models now. A t-test assumes a Gaussian distribution, and we're working with Poisson distributed data right now, so a t-test definitely wouldn't work. So that's why we're using this GLHT function instead. If we give it our GLM object, and then we give it this other argument where we say what I've just written here. So this MCP stands for multiple comparisons. And we're saying, all right, we're doing multiple comparisons of location. All right, we've got three different locations. That's what we're comparing to each other. And I want you to correct the p-values using a Tukey correction. This is similar to Bonferroni, just a different mathematical way of accomplishing kind of the same objective, controlling for multiple comparisons and the errors that you get from doing that. The increased likelihood of finding a false positive. And so with this function here, right, GLHT, give it our GLM, and then say multiple comparisons on location with a Tukey correction. We want to run this, but really we just want the summary output from it, so I'm even going to just wrap that in a summary function and now run it. And what we get here, we can see simultaneous tests for general linear hypotheses. That's what I said GLHT stands for. It's multiple comparisons of the means using Tukey correction. It's got our model fit up here, the formula for our model. And then here are the different comparisons, right? Japan to Alaska, Ohio to Alaska, and Ohio to Japan. Those are the different kind of combinations of these three groups that we're comparing. And what it did really was fit linear models to each of these, or generalized linear models to each of these. And so we get coefficients and errors and whatnot. And here we can see the p-values for each one. The p-value for the difference between Japan and Alaska is 0.001, significant p-value. Ohio and Alaska, however, not quite a significant p-value. It's marginally significant. 0.57 is, for all intents and purposes, very similar to 0.499 or something like that. It's a probability. And so this is an unlikely difference, but it is not technically significant at an alpha level of 0.05. And then finally, the Ohio-Japan comparison is also very significant. It's such a small number that R is just reporting it as less than 0.001. And so here, with this post hoc test, this general linear hypothesis test with a Tukey correction that we just ran, we can see the different p-values for comparing each of these three different groups to each other. And this is how we know kind of which groups are driving this pattern. That it's really Japan and Alaska that are really different, and Japan and Ohio that are really different. Ohio and Alaska aren't that different from each other, so it seems like Japan might be the value here that's really driving this significant p-value for our GLM. And so that's how you would kind of run a post hoc test for this sort of generalized linear model, this Poisson one that's kind of mimicking an ANOVA type test, even though it's not an ANOVA. This is how you would then get a p-value for the overall model, a d-squared value if you're interested in that sort of thing, and then run a post hoc test to see which groups are actually driving the significant result that we got.